Everyone. My name is Mike Nakhimovich. I'm an Android developer at the New York Times, and I'm really excited to be here. I usually spend conferences talking about other people's libraries, but today I'm actually going to be able to present to the world something that we built internally at the New York Times. So overall, as a community, we love making apps. I work on 2 apps at the New York Times. It seems like every new interview makes me make an app as well. There's apps for blog posts, there's apps for talks. We make a lot of apps as a community. And we also love open source. We love it because it makes our life easier. Before, we had to do networking using HTTP URL connection. Now we can use things like Volley, Retrofit, and OKHTTP. Storage has also become easier. We don't have to shove everything in shared preferences anymore. We can use Firebase, Realm, and even SQLite and SQLite if you do want to use SQL. Same thing with parsing. We don't have to loop through JSON objects. We have libraries like Jackson and JSON that came over from web. And there's some new players in the game like Mashi that can automatically parse your data models. So I could even make the statement that fetching, persisting, and parsing data has become easy. We have these great open source solutions that take a lot of the pain away from us. But the thing that's not easy is data loading. Everyone seems to do it differently. So when I talk about data loading, what I mean is actually getting data from an external system onto a user's screen. And now, raise your hand if you think that the person sitting next to you does data loading the same way that you do. Exactly. Yeah. Loading is complicated. One of the reasons it's complicated is because you need to handle rotation. And again, it seems like rotation handling is a special snowflake. We all do it differently. We know that we're going to use these great networking and storage libraries, but where do we actually make the networking call? Does our activity really need to make it? What about retaining data? Where do we retain it? Are we going to serialize our presenters? We can't really serialize our activities. So we built Store at the New York Times to try to simplify loading data. We had a few goals in mind. First, data needs to survive configuration changes, agnostic of where it comes from or how it is needed. So we don't care if you're using Retrofit or Volley, if you're using Firebase or SQL, no matter whatever libraries you're using for your parsing and fetching, your screen should still work in a manner where they will survive the configuration change. Now, activities and presenters should also stop retaining megabytes of data. Activities should be doing activity things. Presenters should be, you guessed it, presenting your data. And stores should be storing and retrieving your data for you. We also feel like offline should be a configuration. Caching should be a standard in our world, not the exception. We shouldn't build apps and then think, how are we going to make this work offline? We shouldn't have bad user experiences that drop connection in the middle of what we're trying to download. Now, at the New York Times, we are building something that is supposed to replace a newspaper. Our users would be really uncomfortable if their newspaper suddenly doesn't work in a subway. We also needed to make APIs that are simple enough for an intern to use, but they need to be robust for everyone to use. We didn't want to have multiple ways to do data loading. All of our data load should be coming through a store. Our team gets bigger every summer. We pick up 3 interns out of a team of only 6 developers. So we need to have these APIs be ones that, within an hour or 2, I can onboard someone on. So then what is our data story? How do we actually work with data at the New York Times? What are our use cases? Well, the most common one is you have a screen. That screen is going to need data. It doesn't care if that data is fresh. It doesn't care if that data is coming from storage. It just needs to be able to display some model onto the user's screen. Alternatively, there are times when you're going to want to fetch fresh data. This is for things like if your user does pull to refresh, or if you have background services or job schedulers that are going to be syncing with the server. Since performance is important, we should really make all of our calls async and reactive. Our screen should load and wait for our data to come in, rather than having all these blocking calls that are dependent on each other. But data is dependent on each other, so we need a pattern where our data loading should also be dependent. We should also have a way where we can hook into in-flight responses. We download a lot of data at the New York Times. Our homepage sometimes is up to 10 megabytes. And if multiple places in their app are all trying to get that same homepage, I think our users would get really upset if we started hitting the network and downloading these huge collections. We should also be able to parse efficiently and minimally. We shouldn't have to parse our network data over and over again. Parse it once and cache it somewhere that after rotation, you'll be able to access that same data. So we looked for patterns. We looked for what can help us achieve these goals. And what we settled on was the repository pattern. What we did was create reactive and persistent data stores. This is that abstraction that is going to manage all of these data operations. When we talk about the repository pattern, what I mean is that we need some kind of construct to separate all of the logic of how you will get data from the network, how you will parse it, from the actual screens that are going to be using that data. Your screens, your activities and presenters should not be parsing. We feel like the repository is that middle tier that will sit between all those great libraries I described and your view layer. This gives you a few advantages. For one thing, testing becomes easy. You can test your data layer mocking your UI, or you can test your UI while mocking your data providers. It'll also make it easier for you to work in teams. You can have someone building your UI that will be calling these stores, and then have someone else actually working on, well, how is the store going to get its data? We also wanted to have some type of centralized logic and access rules. There's all these great libraries. Firebase was something that recently came out that had its own APIs that are different from RESTful calls. But we wanted to wrap everything in consistent access rules and logic. I do not feel that a UI developer should know that I'm getting data from Firebase, or I'm getting data from our New York Times servers, or I'm going to GitHub to get some stats. We should have a consistent API for all of our data fetches. So that's what we try to do by building the store. A store is something that is going to manage the fetching, parsing, and storage of one data model. I'm not talking about having some kind of content manager that everything in your app is going to pass through. I'm talking about making single responsibility stores that will manage one endpoint or one type of data that you're going to get from an external system. You'll have to tell the store some stuff. You're going to want to tell the store what it's going to fetch, where it's going to cache, and how it's going to parse the data. The store will then handle all the logic and the flow around these operations. It's the code that you've been writing yourself for years. Stores are observable by default. They will return RxJava observables, but they'll have a very simple API. This is what I mean that when we have interns start, I don't want to explain to them content providers and all these complicated APIs. I want to show them a few methods, and they should know how to use this. So let's see how we're going to use a store. And I'm not really going to show you at first how you would instantiate or build a store. We'll come from the perspective of the UI. You're just the UI developer working in an app, and you want to be able to fetch data. In our particular case, what I'll go through is an example of loading a pizza onto a screen. So first is our 80% case. We have an activity. When it starts up, we're going to want to get a pizza passing some type of identifier, in this case, a topping, which is cheese. We'll subscribe to the result. When we do this, the store will manage the request. It'll first check, do we have this data in memory? If we do, it'll return it back to the UI. If we don't, it will go to its fetcher and then be able to get that data, cache it, and return it to the screen. Now, this is important because we need to survive configuration changes. So when you rotate, you call the same method. You just call store.get again, passing just a topping that you serialized in save or store instance state, and then you're able to get that same cached pizza again. And just a little warning, please don't serialize your pizzas. It's going to get really messy. We want you just to serialize your identifiers to your data rather than your complicated data objects. what does this buy us? Well, for one thing, our fragments and presenters can become very lightweight. They don't need to be retained. They don't need to manage parsing. We don't have to worry about transaction to large exceptions. The limit of how much data you can pass from one activity to another was just taken down. And you won't have to worry about that if you're only saving a few identifiers for how to get your data while you're rotating or going into a different configuration. Similar, these keys. In my case, the key was just a string, but it can be any POJO. That's the only part of your app that's going to need to be parselable. You don't have to make all of your objects parselable. Speaking of the flow, efficiency is something that is important for apps. Now this is a little bit of a canned example, but say you are calling store.get when you are loading your app from 20 different places. There will be logic within the store that makes sure that only one request will get through, the rest will piggyback on the response, saving precious megabytes. So that's that get case. That's that common 80% case. But somehow we also need to somehow get new data from the network, from a pull to refresh, for example. And that's where fetch comes in. Same thing, you just pass in whatever your identifier is, cheese, and you get whatever your data was coming back from the store. So fetch is a little simpler than get. It's not going to get it from memory. It'll always go to the network. But it's important to see that it will fill the memory cache so that you can call get and get that same data that you got with a previous fetch call. Fetch will also do that same type of throttling. And what we found is that this throttling helps us when we code our apps well, but we had times when actually our developers screwed up. By our developers, I mean I screwed up, and had code that for some reason was trying to hit the network dozens of times on start. Well, your users will not be affected by that. You'll still have to fix your bugs, but at least in the meantime, you're not going to be downloading more data than you need to. The other method that stores has is stream, and this is a little more reactive. So this is an endless stream of data. If you notice when we did get and fetch, we passed in some type of identifier. Stream's a little different. We don't pass anything into stream, but what we will get back is any new pizza that comes through the store. So if anyone calls get and it goes to the network, it'll hit this callback as well. If you call fetch, it'll hit this callback as well. This is great for things like showing a snack bar of a pizza is ready. So that's how we use a store. Now let's see how someone, a different developer, can actually build up a store. And we do this by implementing interfaces. The interfaces are pretty simple. We have a fetcher, a persister, and a parser. So all you really need to tell us is, again, where you will fetch, how you can read and write from whatever file system you're going to be using, and how you're going to transform your data when it's coming from the network. This is an example of what a pizza fetcher would look like. We do want an observable to be returned from this, which helps us stay reactive. So here I'm simply, whatever topping I passed in before cheese will be what is passed to this fetcher, and I'm able to actually pass it to my network client. Like something like retrofit would work perfect in this example. If you're using a network client that is not observable, say you're using OKHTTP, you can wrap your calls in observable from callable, which will give you an observable to return through your fetcher. And since fetchers only have a single method to implement, here's how if you use retro lambda, you can inline the entirety of your fetcher. Now, I don't know about the APIs that you use, but the ones that I use don't return view models. They don't return POJOs. They return some kind of binary format that we can get over the wire. So we need to transform our data when it's coming from this external system before it gets to our user screen. And that's what parsers do. They transform. They have some type of input and some type of output. So here we have a parser that will go from a pizza to a pizza box. Let's say we want to show pizza boxes on our screen. A more common transformation is reading streams or getting data directly from your network. Here I'm using buffered source, which is a type that you can get from OKHTP. From that buffered source, I get an input stream reader and feed into JSON the data as it's coming over the network. Because we let you define what your data types is, you can use a streaming API through your parser. And we do recommend buffered source as the nicest data type to use. Now, this is a really common case. We wouldn't want you to have to write all these parsers and input stream readers. So we included some middleware as well. So if you're using Jackson, Moshi, or JSON, you could include one of these packages and then use factory methods that'll actually return the parser that you're going to want to use. So let's look how our data flow changes now. The purple is the new part. When we get data from the network, we will parse it before saving it to our memory cache. And this is in line with parse once and parse and then save your data, so after rotation, we're not doing these heavy transformations again. We could add offline with persisters. I said offline should be easy, and we made it easy for you. It's a one-liner. We have a file system record persister that as long as you feed us in a buffered source and some configuration of how long you want to persist things on disk, we have a factory method that will start streaming your data from network directly to our file system. The file system is just simple storage. The file system reads, it writes, and it deletes at a particular path. We included the file system as a separate artifact as well, so that if you don't want to use this and you want to implement your own, that's not a problem. As long as you can implement our read and write interfaces, you'll be able to make your own persister. So you can actually start using Firebase or SQL as your persister. And you can work with any types. As long as your persister returns whatever the raw type was that was coming from your network and can give us a Boolean anytime it writes, you can hook your persister into our store. There's a few helper interfaces as well. If you implement these interfaces, we can supercharge our store and start actually clearing things or being aware of records, kind of like the last file system persister was, where it would only stay for a few hours or a few days. So here's our most complicated diagram. I swear I'm not going to keep blowing this out of proportion. So now, after we check whether it's in memory, before going to the network, we'll have this persister layer that we can read and stream to our memory cache before returning it to our user. Otherwise, we will go to network. Ideally, we will stream data from the network to the persister and then stream it through our parser, save it in memory, and return it to our users. So those are the components of a store. And now that we have the different parts of it, let's actually build a store so this little pony has somewhere to shop. So we're first going to take a couple of parsers. You're probably going to have a few different transformations, not just reading a stream. You might need to change your objects or box them or do something else. So what you can do is create a list of parsers. Here we have our box parser and our middleware JSON parser. And then we can start building a store. We have a few entry points. The most complicated one is parse with key, where you pass whatever your data type is for your key, that is that identifier that you pass to the store, whatever your raw type is that'll come from your fetcher, and whatever your parse type is, that is going to be the last parser that is going to go through the chain. So here's that pizza source, followed by our persister that will persist anything for 1 day. We're also adding a prefix so that we can go directly to the file system later and access our data based on some prefix or some key. We'll add our list of parsers. And I actually have a little mistake here. These two should be in reverse. Whatever order you add the parsers to the list is the order that the store is going to be loading the data. So you really want to be adding the JSON parser first, followed by the box parser that will box up your pizza. And finally, we open a store. We get a pizza store that can return pizzas based on keys that are strings. Stores also have a few configurations. You can configure the caches. We can use a memory policy to configure that in-memory cache. Remember, that's the one that your data is inflated already. And this cache can actually get set two different ways, either a number of items or some amount of time that you're going to have data in here. We actually use both of these in our app so that we have some kind of maximum size plus some kind of maximum time that you're going to have. You can also configure your disk cache. So here we're using refresh on stale as a hint to our store, which will mean that if you implemented that record persister or used our file system record persister, it will backfill the cache anytime it has expired data. The other typical case is network before stale. If you have stale data on disk, we also give you the option of first trying to hit the network before returning the stale data to the user. If you are offline in that case, it's fine. It'll return the stale data from disk. It'll fall back to it. So that's how we build stores. And I wanted to show you how we actually use stores at the New York Times. What are some of the examples within our app? Well, first we had interns last summer. And our interns were tasked with building a bestseller list natively within our app. So the New York Times releases a bestseller list of all different types of books. And our interns wanted to make this experience native rather than someone having to go to their website. So first what they did is just built an API. This was actually using retrofit that will return an observable of a buffered source. It'll take a category, which is what type of list they want to return. Next, they built up a store. This store got as its fetcher that API. Its persister is that file system record persister. Its parser is that source parser that's in the middleware. And they can return the store and start using it within their activities. So this was our book activity. When it loaded, all they needed to do was bookstore.get, passing it the category, and they were able to subscribe to the result. This was great. They felt awesome that they were able to build screens that worked similar to how our senior developers build screens. It also was nice that when someone loaded one of the screens and then went offline, they would be able to get that data again. Now fast forward a few months, our interns left, and I wanted our books to actually be available offline without someone having to open it while they're online for the first time. So we have a little background updater where we update stuff overnight. And within this updater, because our interns use the store, I was able to call bookstore.fetch. I actually had a loop that went through all our categories and was able to fill our cache prior to the user needing any of that data. And this was great. I felt like I was able to supercharge code that our interns built. We were all building up to the same thing using a common pattern. So the way that I like to think about it is that data is available when the screen needs it. The UI calls get, while your background services can call, sorry, that's supposed to be fetch, not fresh, to actually get the data from the network and make sure it's available when it is needed. If the background update fails for some reason, you don't need if checks in your UI. By calling store.get, it will go to the network if the data is not available or expired. Another typical case for us is dependent calls. So here we have a piece of code that actually lived within our main activity, and it shows different sections in a view pager. And what's interesting about this is that each section has a name, like homepage, but before I can call my section front store, I needed to get metadata from our feed. It is some large object that we have that we get from the network that has metadata for each section. So now I can just use RxJava concepts like map and flat map to get from the feed store get all the way to my section front store get. And what's nice about this is that I'm calling get in both places. If the feed wasn't loaded yet, it's fine. It'll go to the network. Similar for the sections. There's another way that you can set up relationships, and it's by subclassing stores and overriding what the get and fetch methods do. So we recently built a 360 video implementation, and our API wasn't exactly what we wanted to be able to cache all of our data. We had some endpoint that can return all the data for a single video. We also had an endpoint that can return a playlist of all the videos for that day. Well, our app is offline first, and somehow I needed to combine these calls. So the first thing I did was create a video store. And, got too excited. I created a video store, passed it a fetcher and a parser, just like all of our other stores. But now, when I build this video playlist store, I'm subclassing real store, which is actually what you get back from the store builder, and I'm also passing in my video store to my video playlist store. What this allows me to do is override how get works for a video playlist store. So now, anytime I need to get a playlist, I can call super.get to get the actual playlist. I can then get whatever video IDs are from there and start fetching from my video store all of those different videos, flattening it back into a playlist that contains all the actual video data, and now our 360 stuff can work offline. Another common case within our app is listening for changes. And this is where you want to be notified when a certain store has something go through it. So in our case, we'll go back to the section front store. We have a view pager of sections. So when a user is using our app, they only will have one section on their screen at a time. Each one of these views within the view pager will be subscribing to the section front store stream and filtering only the section that it wants to see so that it can handle a section change. So this works really well because we have some other call within our app which refreshes sections. It'll get only the sections it needs to update and then kick off a fetch request for each one of those sections. What's neat about this is that when this store's fetch is called, the views that got updated will know that they need to handle the change, which we usually just show some kind of timestamp or something, hey, your tab got updated, without having to show on all 9 tabs that are off screen that they got updated. User doesn't see that. Another typical use case that actually came out of every single QA after I give this presentation is how would you do pagination? So I have an app, maybe like Facebook, where a user will first load the first page, and then as they're using the app, they're going to load more and more pages. When you rotate, you're going to want to get to whatever that last page is and load all of the pages. So how do we do this? Well, actually, the example I go through is our comments. So we show comment pages within our app. We organize each comment page as 10 comments. Our comment store is, again, a subclass real store, which now has a helper method called getPages. And what this will do is make an observable that'll go from 1 to however many pages are passed in as a request. And then we can flat map each one of those pages to an actual comment page and return to our UI that stream of comment pages. So this is what our UI would look like. When we have our comments activity, we'll start on page 1 when the activity loads. We'll call store.getPages, passing it our comment request for a particular article, and whatever the page was, which was 1 in this case. We'll subscribe to the results so we can show it on our screen. We'll also have this getNextPage functionality. And get next page would be for the use cases of when someone hits the bottom of your recycler view, you will call that. We will make our page go up by 1, and now just get that page. We're not going to call the same method that gets all the pages, just get that one page. When our app will rotate, we will save whatever number of pages we've shown. If it's not equal to null and we have that state, we'll restore this. Let's say we'll restore that as 5 this time because we've already shown 5 pages. Same code as before when we call store.getPages. If current page is 5, now it's going to give you the stream of all the pages you had prior to rotation. Pagination becomes a breeze. So finally, how did we actually build the store? Well, I'm sure you guessed, we used RxJava for our API, but we also used RxJava to do some of this management of different data sources. So when you call store.get, we're actually concatenating together the caches and your fetcher and doing a take one. Because we're doing a take one here, if cache returns something, you will never hit your network. You're not going to be at the same time getting both of those sources. We also have some helper other APIs that I didn't talk about, like get refreshing, which anytime you call clear, will actually repeat whatever that get request is. We use Guava caches for the memory caching. And don't worry, we painstakingly removed the caches from Guava so you don't have to add all of Guava to your app. You should still ProGuard, and you will still get some savings if you do ProGuard, but we did make our own cache artifact that we also released. And that's what happens with that memory policy. It actually goes into a cache builder. We use another Guava cache for the inflighter, and that's the thing that will block. One of the powers of using a Guava cache is that it'll block all of the requests. If the value does not exist in the cache, it'll block until it loads it and then propagate it to anyone that calls that. Yeah. Our simple file system was built using OKIO. We went with OKIO because of these buffered source interfaces, which made it really easy for us to stream data. There's times when we've downloaded 30 to 40 megabytes of data on a fresh install. Don't worry, only if the person was on Wi-Fi. And the crappiest of phones were able to handle it. We never stream more than a few bytes at a time, rather than loading all those expensive JSON strings into memory. And that's it. We'd love your contributions and feedback. We were amazed when we released this that people actually started contributing code back, and this was really fun for us. So if there's something you'd like to see in this library, come find me or open an issue, and we'd love to make this work for your use case as well. Thank you very much. Questions?
Hi. So we see that we can choose between taking the data from the persistor, or then from the network, or the other side. So is there any way to know from which one it gets? Because maybe if we get from the networks and it fail and you get from the memory, we can want to print a message to tell maybe it can be outdated data or something like this.
That is not a feature that is built in, but because you are returning your data, you can box whatever your fetcher is returning and add additional metadata as it's coming through the sources. So because we returned a pizza from our fetcher, we could have actually returned a pizza container that has from network as a flag. When it comes from your persister, you can flip that flag to coming from the persister. But that seems like a great feature, and I'd be open to suggestions of how we can actually add it to the store.
I will look into it.
Here? Yes, hey, thanks for the presentation. I had a question about the store. Can you list all the objects of a given type in your store? And can you query the store? Let's say you want all the pizzas that have mushroom on it. Can you get just the sublist of all these pizzas?
From the memory, you cannot, but because you are passing in a persister, if you use our file system persister, there is a read all and a clear all that'll happen. So you won't be able to know what is in memory, but you should be able to query what is on disk. Good question. Getting some exercise.
Hi. Just want to know, in case of timeout exception, did the store library implement a kind of retry policy?
There is no retry policy on the store, but if you use a network before stale, if you do timeout on the network, it'll give you whatever the last thing you had, which was on disk. But overall, if you're using OKHTP, it does retry or try to retry if there are issues with it. Or when you return your GET request, you can add a Rx operator, retry with some type of policy, or just something like a retry too. It's one of the reasons why we wanted the API to be built with RxJava, so that all of those functional concepts and all those little helper methods, we did not have to implement ourselves, but it'll be painless for you to add.
Okay, thank you.
Yeah, thank you for the presentation. It was really
Oh, thank you
great.
for coming.
I have two questions. The first one is, since when are you using stores in production? And the second one is, how does it help you to increase the quality of your code in the app?
Yeah, absolutely. Personally, I've been using stores in production for the last 3 jobs that I've had. New York Times was the first time that we were actually able to standardize it and put documentation around it. Currently, it is powering our newsreader app for the last 2 years that has, I think, like 20 million users. And our crossword app is using it with SQL rather than our file system. It seems fairly stable. We try to wrap everything in tests. If there's something that is missing, you can obviously add tests to make sure that it works, but this is very production ready. It also, to answer the second part of your question, it did help us a lot with architecture. So before we had, and I'm sure a lot of apps have this, something like a content manager, a single class that everything passes through. And it looked like there were it was something that either everything depended on or it depended on everything. Stores helped us be more feature vertical in our architectures, where I have a new feature like books. I make the fetcher, the persister, the parser, the store, the presenter, and the activity for book, and it is not dependent on anything else that is being used within the app.
Hi. I had one question about concurrency. Say you start loading something on the background, and then you change your configuration, but the background hasn't returned result yet. How do you manage concurrency calls, or do you call twice the same
So
API?
we'll call the same store get before and after rotation. We take it case by case. If we feel like this is an area that people rotate and we are loading large objects like our articles, we will actually not unsubscribe when we are rotating so that that last call finishes before the next one starts. Now, these could have all actually been Rx singles and not observables. It's going to be hard for you to leak. These are not endless streams besides stream, so that you don't actually need to be as careful unsubscribing. So we keep the calls alive when we rotate in most of our use cases. Wonderful. Thank you so much, everyone. Enjoy the rest of your day.